Thank you for the introduction. Yes, and thank you for the invitation. I'm looking forward to this conference for more than a year. So I'll talk about something quite elementary compared to the other talks this week. Okay, this is a joint work with Zhiyu Tian. This has been published, I think, 2 or 3 years ago. Let me start with the classical setting. So it's a classical or original McKay correspondence. So by classifying dimension 2. The main object is a finite subgroup of the group SL2C. Okay, finite. Such groups are already classified. I will talk about the classification in a minute. But once you have such a finite subgroup, you can look at the quotient. C2, there is a quotient by G. There will be a unique singular point in this quotient, namely the origin. So this is a singularity, isolated surface singularity. It goes on many names. I think I will call it Duval singularity, but also known as Kleinian singularity, Kleinian singularity, canonical singularity, rational double point. If I have enough space here, rational Gorenstein. Let me try. AD singularity. Singularity down here. Yes. Of course, these are the roots of the singularity theory. All the notions generalized to higher dimensions in somehow different ways. But you can all see the roots in 2 dimensions. So this is the singularity, right? And of course, as an algebraic variety, it's just given by the spectrum y. It's the affine variety. Defining the singularity. Right. Then in 1870s, I think, Klein already proved that studied this invariant ring. This is somehow one of the most popular subjects in that period of time. And he computed certain invariants, and he in particular proved that this is generated by 3 equations, generated by 3 equations, I guess 3 elements, I would say, subject to one relation. So in the end, this is always a hypersurface singularity in C3, okay, defined by one equation. And then in 1960s, here comes Duval. He systematically studied this singularity by computing, in all cases, by first classifying all the G's and then computing all the invariant rings and compute the singularity type and study the resolution. And if I denote by C2G, the singular variety is always a quotient singularity. Then, if I take the minimal resolution, so for normal surface singularity, you always have a minimal resolution, and more or less by the definition, you see that this is actually a best resolution of singularity, namely it's a crepant singularity. This is crepant in this case. So here, crepant means that when you resolve the singularity, you doesn't add any exceptional divisor. There's no discrepancy. So it means the canonical bound. First of all, the canonical bound of the quotient is well defined. Gorenstein appears there. And then when you pull back, it's actually equal to the canonical bound of the smooth surface. So it's called crepant, meaning that there's no discrepancy. And then if you look at vertically, then if you look at the fiber over the singular point, you get the exceptional divisor. Right? And you can show that E is a bunch of -2 curves. A tree of -2 curves intersecting each other transversally. Here by -2 curve, I mean an embedded P1 with self-intersection number -2. With a smooth P1 with self-intersection number -2. And I don't know the time. I guess it's which
37.
Huh?
37.
No, I'm looking at the year for McKay. I think it's around the 80s. I'm pretty sure. Around the 80s. Thank you for anyway. McKay discovered a relation, a very close relation, a relation between. So I have bigger geometry of, you can say the equivariance geometry of G on C2 or the singularity of G C2 over G, or the motives. Let me put it hidden here. Motive. That between this and the representation theory of the finite group G. Okay, so this is a hidden motive for representation theory. Then I'm trying to give you the classification of such group and how these things works in the concrete cases. So here's the classification. Actually, the classification is irrelevant for this talk, but it's so beautiful that I can't resist myself from giving you that. How many columns do I need? Let's see. Sorry, probably I need bigger. So here's the group G in SL2C. Okay. Of course, this is a finite group, so I can assume up to conjugation to put it into a maximal compact. So I will put SU2. It's really the same thing, or spin through. Here is the group. Then, I will probably give you the order of the group and the singularity in terms of equations. 2 over G and the origin. How can we see that as a surface singularity? And also the exceptional divisor E. Okay, E is this E when you resolve linearly, practically. And also in the end, I will do something more interesting. So the group, the easiest group that you can guess is the cyclic group, right? Z over Z. Okay. Then, in that case, and always N, I have to tell you. In that case, the singularity computed by, I guess already by Klein, is defined by equation like W square, U square, and if it's order 2, then it's a cone over the conic, so it's Vn, it's Vn 0. Okay, this is a very easy exercise if you want to compute yourself. Okay, xy. Then you look at the invariant Z2. Of course, I mean, the D2 action is sends x to minus x, y to minus y. So the invariant elements are generated by these kind of things, x square, y square, and xy. And they, if you call this, I don't know, you call this W, call this U, this V, then this is just this W, U, V, subject to the condition that the W squared is equal to U times V. Then you do some change of variables, you get U square minus or plus V square. So that's the case for n equals to 2. And when you, so you know this singularity, how does this look like? It's a cone over the smooth conic curve in the plane. So when you resolve the singularity, you blow it up, you get, you blow it up, you get, this is not very faithful picture, sorry. You get the exceptional curve here, which is P1 with self-intersection -2. So the exceptional curve, I'll just draw a line with -2. So this is the case for n equals to 2. So there's one copy of -1 curve. But if we're in arbitrary n, you will get a chain of -2 curves. Okay. So it's -2, -2. Okay. If you like to draw the dual graph, of E, obviously you get chain. Yeah? This edge, so each vertex may represent -2 curve, and an edge between two vertices means that there is a transversal intersection. Okay. And then the second group is so-called binary division group. It's called binary dihedral. Yes, binary dihedral group. So yes, I can say that I use this space. So if you have a subgroup G inside SU2, then SU2, as you know, it's a spin 3. So then SO3, it's a double cover of SO3 R. Then you can look at the image, let me call it G bar. It's a subgroup of SO3. So whenever you have a finite group of SO3, you can look at the orbits of a point. Then you must get some the vertices of some regular polyhedron, right? But you know the classification of regular polyhedron in 3 Euclidean space. It's like tetrahedron, cubes, octahedron, icosahedron, but the other word I cannot pronounce. Dodecahedron. These are the regular polyhedron with 12 faces of a regular polygon. Okay, so whenever you have this group, if it contains the kernel of this surjection, then it's a double cover of certain isometry groups, rotational isometry groups of certain regular polyhedron. So that's why, okay. And also there is a degenerate regular polyhedron in R3, which is the regular polygon with 2 faces. That's why it's called dihedral. It's like a regular polyhedron with 2 faces together. And the binary means that it's the double cover of that. So this is binary dihedral, and the dihedral group is of order 2n, so it's order 4n. And if you look at its equation, it's also a double cover of something like I guess n, oh man, it's b squared u0. So here, I think this is n. Yes. And if you resolve it, you will get something like this. Then you will continue in a chain. Okay. So the dual graph would look like this. Okay. And then you can continue with your favorite regular polyhedron, for example, binary tetrahedron. Tetrahedral group. Tetrahedral group, which is the double cover of the isometry group of tetrahedron, which is isomorphic to A4. So it's 24. Order 24, and I think I don't remember the equation. Sorry, 3, 4. It's actually quite. And yeah, I won't draw the dual. I won't draw the tree of -2 curve, but I will just draw the dual graph of that. As you already see the pattern. Okay. And then we have binary octahedron and the binary icosahedral group. So it's binary octahedron, binary icosahedral group. Okay. As you already guessed, this is type AN. No, actually n-1. A1 is correct singularity, and this is yes, n plus 2. So n is at least 2. This is n at least 2. This is E6, E7. So that's why it's called AD singularity, because in the classification, when you resolve the singularity, you'll get the dual graph, which is AD type. Good. Yeah, the order is to compute. 48, 120. Maybe I'll need the equation here. You can find it any standard textbook or surface. Okay, so this is the classification. So then I can state the theorem of McKay for eigenvectors. So what is the precise relation between the representation theory of those group G and the exceptional divisor DI? Now, while I'm erasing the board, please compute the number of conjugacy classes of G in the case that you can. And also, once you finish, please compare the number of vertices there. So the theorem of McKay, there is a bijection. There's a bijection between non-trivial irreducible representations, usable representation of G, and components. I can also compute irreducible. So if I denote by rho and the component of E rho under this injection, such that so this bijection satisfies several properties. For example, E rho intersecting with itself, as I told you, it's -2 curve. Also, E rho 1 intersect E rho 2. So these are two components in the resolution. So for rho 1, different from rho 2, so non-isomorphic representations. Then this is 1 if rho 1 and rho 2 adjacent. Yes. Here, adjacent means 0 otherwise. Here, adjacent means that rho 2 appears in the representation rho 1 tensor C2. Rho 2 plus something else. Okay? Because here C2 is the natural representation of G that you have in the beginning, because G is a subgroup of SL2C. So actually, this is symmetric relation. If rho 2 appears in this rho 1 tensor C2, then rho 1 appears also once in C2 tensor rho 2. And also, there are more close relations like the dimension of rho I of rho okay, is equal to the multiplicity of the so-called fundamental cycle of the singularity. So that uses a little bit of singularity theory of E rho in the fundamental cycle. So it's really geometric on the right-hand side, fundamental cycle of the singularity. Fundamental cycle is the least, the minimal cycle that is the divisor of holomorphic functions around a neighborhood of this exception divisor, if you're curious. Okay, so that is McKay correspondence. What I want to say. Yes. And then geometrically, there are, after McKay's discovery, there are several ways to see this correspondence geometrically. So McKay was doing this only combinatorially. So this is Gonzalez, Springberg, 83. So basically, goes as follows. So you have C2 over G, quotient of C2, and you have the resolution Y, so crepant resolution, minimal resolution. Then, given a representation of G, it's like a vector bundle over BG, right? That's topological equivalence. Then you get a vector bundle over C2 over G, as a orbifold. So in some sense, equivalently, you get a vector bundle over C2 with a G action. So if you take the fiber product, actually they take the reduced fiber product, reduce the fiber product, Z. Then you get a G vector bundle, you can pull back to here, so you get a G vector bundle on Z. Then you push forward, like G invariant push forward. So you push forward the G vector bundle, and you get like a coherent sheaf, vector bundle, yeah. Then you take the G invariant. It will be a coherent sheaf on Y. Then you take the first Chern class, you get a divisor on Y. That will be E row. Okay, so that's how the correspondence goes geometrically. Of course, they express everything in cases, but that's basically the idea. Okay, so here is the classical part, I think. Then here comes the Miles rate in values. Okay. He suggested another way to interpret this McKay correspondence, namely, so observe that Y is a homotopic deformation retract to the exceptional divisor. So McKay correspondence just says that the set of irreducible representations indexes, the set of irreducible representation indexes homology class. So the index of basis homology. Right. So here, why now I'm not excluding the non-trivial, not excluding the trivial representation because now I add H0. Okay. So H2 are the irreducible representations, and you let the trivial representation index the fundamental class. But also in the new way, you can say, okay, conjugacy class is G index basis of the cohomology of Y. Then Miles rate says, okay, so that means that we have a vector space isomorphism between the cohomology of Y and the so-called inertia of the quotient. I don't know if I should put brackets. If you unwind the definition of the inertia, it's just a vector space based by conjugacy classes of G.
I mean the inertia stack.
Inertia, yeah, this is the inertia stack of this quotient stack. Then the coarse moduli space is just some contractible space indexed by the conjugacy classes of G. So Miles rate says, okay, this bijection says that there is a vector space isomorphism this type. Now, a key observation as a starting point of my talk is that both sides has a multiplicative structure. We want to see whether we can make that isomorphism compatible with the multiplicative structure. Okay, so here is the observation by Chen. One. This is completely general. So Chen says that for any complex orbital X, there is a natural natural cohomology ring. Denoted by H or star X. Let me be vague about the coefficients. I will come to that later. So let me tell you something about this orbifold cohomology. Okay, it's called orbifold cohomology. Somebody calls it Chen-Ran cohomology. Yeah, I prefer that cohomology. As vector space, it's very easy. As vector space, this guy is just the inertia, the cohomology of the inertia stack. But for a cohomology of a stack, I always understand as a cohomology of the underlying singular space. So I'm using at least rational coefficients. Okay, no integral coefficients, please. So, but I'm actually slightly lying here. The grading is not exactly the cohomology of this inertial stack, but with some shifts called age. But I don't want to address this point at this talk. But you just have to know that as an ungraded vector space, it's just this guy. But somehow you grade the elements differently. But the key point is there is a product structure of this cohomology. So the ring structure on this orbifold cohomology is defined as follows. The ring structure is, let me first about it's highly non-trivial. And related to the motivic theory, but I can say it's just so the analog of the multiplicative space M03 bar with X actually if you look at the curves that it has no class, 0, and this space has 3 evaluation maps to the inertia step. So if I put a variety here, this moduli space of genus 03 point, there's a stable maps from the genus 03 marked points to X, actually its evaluation maps to X, right? But in the static case, the natural evaluation maps goes to the inertia step. Now, there is, as in all the Wheeler theory, this moduli space might be weird to high dimension, but there is a virtual fundamental class. So I will just put it here of the right dimension, like a virtual fundamental class defined by some obstruction theory. Then, if you have 2 classes in the inertia space, alpha and beta, you can point it back to the moduli space, cup with a virtual fundamental cycle. Then you push forward to the third factor. That gives you a binary operation, right? And the non-trivial factor that this binary operation is actually associated and defines a ring structure. So this is basically the orbifold cohomology ring. So now here's the question. We have a ring structure on the left-hand side and on the right-hand side. Can we make, let's take star, can we make star meaning an isomorphism of algebras instead of just a vector space? However, the answer is yes, and this is a baby case of something proved by Kaledi. But here, let us remark that this isomorphism is first of all it's only cohomological, right? It's a but here star is local. Okay, I'm treating just one singularity and the quotient of vector space, cohomological. Here the star is only additive. Okay, it's a vector space. So this Chen story and the theorem of Kaledi tells you that you can improve an additive feature to a multiplicative feature. And in the sequel, I also want to improve the cohomological isomorphism. Yeah.
So in this case, that's the shift of grading.
Yes, because the virtual fundamental cycle is defined by some Chen class of certain vector bounds on moduli space. So when you pull back and push forward, the degree won't match if you use the older degree, the older grading.
But I mean, the star there, it was an isomorphism grading vector spaces, but if
No,
you change no? I know. Okay.
No, not even here.
Okay.
So yeah, it'll be weird without star. And I will improve cohomological to a motivic, but this is not very hard. And the local situation to global, like for 2-dimensional orbit. So star fits into the conjecture of 1. Runs crepant, runs cohomological crepant resolution conjecture. It says the following. So if you have Gorenstein orbifold, it means that the underlying post-moduli space has Gorenstein singularity if y to the post-moduli space of the orbifold is a crepant resolution. It's in any dimension. Then we have an isomorphism of complex algebras, so the coefficient range is quite big, as you can between the cohomology of y and not quite isomorphic to the orbifold. So here's not the conjecture, but the conjecture is with some addition. Oh, I don't forget. So here I have to modify this cohomology. It's actually not orange. It's a quantum corrected cohomology. Yeah, I will explain why this is not relevant then I will explain why Canadian's theorem is the local version, local two-dimensional version of Rhine's conjecture. So here you see in quantum connections on the cut product. So it doesn't change anything on the vector space. And then there is original cut product. Now we want to modify it with Gromov-Witten invariance. With Gromov-Witten invariance for actually the contracted curve. So this is a singular variety y to the bar of x. It will contract certain curves. Basically, in our two-dimensional cases, the exceptional curves. If you look at all the Gromov invariants of these contracted curves and put them in a smarter way, you try to modify the cut product in a certain way, then there will be, the conjecture is that there will be certain isomorphism of CL. However, the reason that I don't have to be precise about all these Gromov invariants is that in dimension 2, quantum corrections vanish. There's no quantum correction, so you can forget this green hues there. So the reason is also very simple. The reason is that if you look at like space of y with like a contracted curve, contracted by f. F. Then yes, the virtual fundamental class is the pullback of the virtual fundamental class of M00. That's by general axioms of the Gromov theory. But this guy has virtual dimension negative, actually minus. Okay, so beta times canonical y is contracted, so 0, dimension y minus 3, so it's minus 1. Okay, so this virtual fundamental cycle M00 bar is minus 1, so there's no virtual fundamental cycle. This cycle is 0, but by general axiom, this is also 0. Okay, obviously pi is the stabilization from M03 bar to M003 bar, M00 bar. So in any case, in dimension 2, there is no quantum correction. So two-dimensional cohomology crepant resolution conjecture is this without these cubes here. And this is exactly our theorem. Oh, sorry, I meant not. So the main theory is the following. Is the motivic version of Rice conjecture. In dimension 2. So more precisely. Please, okay. So X is two-dimensional orbifold stack with only isolated static points. This is actually a valid condition because in codimension 1, if you have a stacked ocean in codimension stacked locus in codimension 1, the underlying modular space is actually smooth. So if you always take the most economic static structure of a Gorenstein surface, then this is always the case. Okay, so you have two-dimensional thing. Then, if you look at this comodular space X has Gorenstein singularity. And that y to x is the minimal resolution. So it's a surface, right? Normal surface. So here minimal implies crepant in this case because of Gorenstein condition. Then we have an isomorphism of orbifold motives for x with the motive of y as algebra objects in the chomel. With complex coefficients. Why am I using chomel motive? So okay, I should have used like a mixed motive, but just to be in this more classical category, let me put proper here. But the theorem works for any non-proper two-dimensional case, but then you have to use mixed motive, DM, etc. But that doesn't change anything essential. Okay. So here's the statement. Now, as you can see, this is indeed the motivic global version of Ryan's conjecture, and making the original McKay correspondence multiplicative because this is as algebra objects here.
When you take John Moses with Q coefficients?
No,
No.
that won't work. So you will see in the isomorphism, I will.
C coefficients.
Yes,
That's what the
yes.
C means. Okay.
Yes, yeah, you will see that coefficients, but I'm using at least contain some algebraic numbers. Okay, in the last 5 minutes, I will probably sketch the proof. So I haven't defined what is orbifold product more seriously than just like M03 bars. But in a two-dimensional case, it's actually down to earth. Everybody can understand. So, okay, now we have two sides. We want to prove that they are isomorphic. So let me start with the left-hand side, orbifold side. So in this situation, okay, just to simplify a little bit the notation, let me be in the global quotient case. So let's say X is on the form S over G, where G is a finite group acting on the smooth projective surface as such that all the stabilizer group on a fixed point lies in the SL of that tangent space. Okay, so it's gorgeous. Okay, so orbifold side is the motive is like this. Orbifold of this X is what kind of note SG, G invariant, where HSG is given by the direct sum of G and G. This is actually HS plus all the G in G, but not identity, and plus any X in G, in SG. This is a fixed locus of that element G, and I put a Lefschetz motive here. I will call it L, so it's Q minus 1 for me and Q one for most of the people in the audience. This copy is of Lefschetz motive. I will just give it by XG. If you change the summation slightly, you will get X in S. Singular points won't contribute here because I'm using a stabilizer minus the identity element. Okay. And the product, there are in many ways you can make the product, but let me say that if you multiply HS to itself, then you get the usual cut product of S. If you multiply HS with indexed by XG, then you get to the same place XG. And so this is a Lefschetz motive. So an arrow of this type is just a zero cycle of S. So this is given by the class of X child 2 of X. Okay, it's a kind of natural. And then the most non-trivial product goes here. So if you multiply a Lefschetz motive with another Lefschetz motive, then only non-trivial piece will appear in XG and XG minus 1, and it will land to the first factor HS. And then, this is a Lefschetz motive. So O minus 1 cancels O minus 1 for me. So O minus 2. So it's a child 2 element. This is again given by X. So the product is completely down to earth. Orbifold side. So the product is completely down to earth, and also the G action I didn't say, but it's the natural G action that you can imagine. Okay, on the first factor, you just act by G. On the other factors, you just permute these sums, right? Yeah, the orbifold side, now the resolution side. Oh, no, sorry. So the resolution side is about the motive of the Y. So if this is actually a semi-small resolution. Okay, so the cohomology space is just the quotient S over G. And then whenever you have a semi-small morphism, you can have a motivic decomposition. And also the intersection product here is also well understood because we know all the intersection products between section divisors, etc. Let me write you the answer. So it's the G invariant part of the following thing. So it's now I want to index all the exceptional divisors. Here is the place where the classical McKay correspondence comes in. Okay, because you want to understand, for example, divisors of Y. These are the exceptional divisors indexed by irreducible representations of G. So here, yes, so it's S, and then rho in the non-trivial irreducible representations of GX. One copy of Lefschetz motif. Okay, so here the G action is permuting the factors here, and the product. So here on the first side is also on the first factor, it's, as usual, the cut product. And if you further multiply to HS with a Lefschetz motif, and this is given by cycle. Co-dimension 2 cycle. And the non-trivial point is that if you multiply two Lefschetz motifs indexed by rho 1 and rho 2, they again ends in HS, but given by the following formula. Given by if rho 1 equals to rho 2, so it's minus twice of x, just like in the McKay correspondence. If rho 1 is different from rho 2 but adjacent, then it's 1 times x and 0 otherwise. And it's 0 otherwise. Now, if you give me 1 minute more, I can tell you what is the McKay correspondence like in our so HY is the G invariant part of this algebra object, and the orbifold motif of X is the G invariant of that part. So I only have to give you isomorphism between these two algebra objects. Well, reducible GX. Rho goes to HS. CS. G in a GX but not identity. With the resolution side orbifold side. And then there's phi is ID on, yeah, okay, phi is a diagonal, blocking diagonal, diagonal block matrices. So here ID on, you can guess. And for each x, so it only happens when there is no triple stabilizer, I have to give you a matrix between this, right? G is given a matrix because these are Lefschetz motifs to give a morphism just a matrix, right? Given by the matrix, which is 1 over square root of GX, here is a complex number, chi rho 0 G minus 2 of chi rho G. On the end, it's entry indexed by rho G. So this is a square matrix. And as you can see, the main part here is the character. And these are actually constant on this matrix, only depends on x. And these are like column constants. Okay, so it's essentially a matrix of character table. But as you can see, oh wait, rho 0 is the natural natural expectation. As you can see, this is a real number because it determines 1. But anyway, this is it's a complex number after you take the square root, and the whole thing is a complex number matrix. And then you show that phi is additively isomorphism. That is not very hard. And the main part that I wanted to show, but I don't have time, is that to check that this is actually multiplicative. So if you take two elements here, and then multiply using this formula, you will see that it's indeed a ring isomorphism. And also you can check it's compatible with the G action. So after taking G elements, it's also an isomorphism. Yeah, but I think I will stop here. Sorry for taking too much time.
Okay.